Yeah, so I'm a senior data scientist at Pacmed, and I'll talk about Pacmed in a second. I do have a background in biomedical engineering and surgical robotics. And before Pacmed, I worked a bit in research, in deep learning, and then at Bank here in the Netherlands. So also a bit of fintech. And now I work at Pacmed. So Pacmed is an Amsterdam-based startup. We just moved to a beautiful office in the Pipe. It was founded in 2015, and we are about 30 employees right now, and we are a mix of engineers, data scientists, but also former or current doctors. And we also expanded with a bit of a legal team and so on. And what we do is we developed AI-driven or machine learning-driven decision support tools for the intensive care. And this is something that I'm going to talk to you about today. Before we start, so I want to answer this question. Why are there so many machine learning models developed in literature, but so few implemented in practice? Now, this applies to many areas, but particularly in healthcare. And it's a big problem, right? Because, okay, so many cool things are being developed, are being researched, but then actually you go to a hospital and how many times have you been treated with a machine learning powered software? Probably very few times. This is one of the many papers that tries to address this problem. And one of the things that is highlighted is how the lack of ability to demonstrate the fact that these models are safe and effective is basically hindering the spread in practice of these models. And one of the main ways in which we can try and actually enhance this process is by making sure that these models can be surveilled, their calibration is monitored, having a robust infrastructure that makes us able to be sure that the model is doing what it's supposed to do over time when the model is in production. This applies to every field I can think of, but particularly when the life of patient is on the line. So today I'm going to give you a quick introduction to Pacmed Critical, which is our flagship product for the intensive care. And then I will explore three main challenges that we face when implementing machine learning for life and death situations in the intensive care. And I'll show you what we have come up with to address each challenge. So if you don't know what the intensive care is, I don't know where you've been living for the past 2 years. But basically, it's where patients that are in critical conditions are treated. Now, this became very famous with COVID, but even before COVID, a lot of patients go to intensive care, sometimes after surgery, but sometimes because of very acute and sudden conditions. And an interesting thing is also that patients are monitored continuously. So this is just a subset of everything that is measured in the intensive care. Some of these parameters, so in my presentation I will talk about parameters, and I mean clinical parameters, so each of these is a parameter. Some are measured every day, but some are even measured every minute. So obviously, implementing software in the ICU has great potential because it really is a critical environment where you can make very important decisions, and there is a lot of data, and you also have very nice stock photos for business people to be excited about our products. So this is a screenshot of our software. So this is something that doctors look at when this is integrated in their software when they look at a patient, or in this case, at a set of patients. And these are all the patients that are currently in the intensive care. So you see here patient information. And this is the outcome measure that so this is the main information that we provide the doctors, and is basically the risk that if the patient is discharged, so it's sent away from the intensive care, whether home or usually to another ward of the hospital, the risk that that patient is going to come back to the ICU, or that the patient will die within 7 days. This actually happens very often. So for an average hospital, about 6% of patients die or get readmitted, which is obviously very bad for the patient and for the hospital because we occupy extra beds and extra costs and so on. And then we provide other information, which I'm going to talk about a bit later, such as whether the patient is currently on life support, because that influences the decision of whether the patient can be discharged or not. When you click on a patient, this is what you get. So you see here the curve of the probability of readmission and mortality over time. And then here we really try to explain what the model is doing as much as possible. So these are the features. And we try to tell the doctor, okay, this feature contributed positively or negatively to the prediction. By the way, these are all fake patients, so don't worry. This is the current prediction, and we also have to give a big red warning saying, look, these features are just a correlation with the outcome. They're not a causal. There's no causal relationship, so don't try to increase the sodium in the patient blood thinking that this is going to improve the condition. You'd be surprised, you know, if it's there, there's a reason why it's there. Just a quick overview of the software. It's not super important, but it's I just want to give you an idea of how the data flows. So we offer both cloud and on-premise installation, and the important part is this part here, which is how the data flows from the electronic health record of the hospital to an intermediate database that we can access to then all our ETL pipeline, feature engineering, prediction, and front-end. So this is how the data flows from the hospital to the hospital again, eventually in the front-end that I just showed you. It will become important in a second. So this is an overview of how the software works. Now, once this is implemented, as I said at the beginning, it's very important that we are sure that the predictions that we provide to the doctors are safe, are usable, that they're not going to make decisions based on faulty data. Now, the first concept is data validity. So how can we ensure that the data we process is valid and correct? The second one is interpretability and auditability. Can we explain why the model gave a certain prediction? And the third one is prediction validity. So given a certain prediction, can we sure that that prediction is valid, and can we trust it, and can or should the doctor use it to actually make a certain decision? So let's talk about data validity first. Now, we identified three main areas. There are more, but I think it is a good generalization. So the first one is data drift. Second one is data extraction errors and registration errors. Back to the diagram of our software. This is a simplified version. This is when we install the software on-premise, so we don't have a lot of components that are needed when we install it in the cloud. This is what we develop and maintain. So from the database that the hospital maintains, we then extract the data, we map it, we process it, we create features, we do the predictions, and yada, yada, yada. So we are pretty confident that this works. We have all our tests, all our integration tests, system tests, and so on. But what happens there? So the hospital, we obviously cannot access the data from the same database that the hospital software accesses directly. I mean, I say obviously, but this is usually the case. So what they do, they extract the data for us and put it into an intermediate database. And obviously, these are all, I keep saying obviously, it's not that obvious, but this whole infrastructure is created and maintained by the hospital. So we have no idea what's going on there. But errors can happen and do happen. So how do we monitor that without being able to monitor the infrastructure? So the first concept is data drift. I'm sure you are all very familiar with it. So it's the changes in data distribution, so in the distribution of the parameters over time. An example, so due to COVID, patients in the ICUs recently in the past year or two are very different from all the patients that were in the ICU in the past. So if we train a model on patients from 2006 to 2018, and we try to apply it to current patients, then we will have problems. One example, patients with COVID might have a much higher respiration rate because they struggle with breathing. And while in the past this was correlated with a negative outcome, it's not necessarily the case for COVID patients. So the model will have learned that a certain feature is correlated with a negative outcome, but then this is not the case, and you will have a very skewed distribution of the data that is different from the training data. The second one, and this one is not really anyone's fault. It's just things that happen. But we can't fix this. We just be able to know that it happens to then do something about it. This is registration changes. So these are all the changes that the hospital does to how they record data and they store data. So for instance, the hospital starts registering heart rate with a completely new parameter ID and a new parameter name. This parameter ID didn't exist when we performed all the mapping of the parameters at the beginning. So suddenly, we don't have any more heart rate. We don't know where the heart rate went. They forgot to tell us, and now the model thinks that heart rate is not measured for any patient. And obviously, the performance would drop massively. The third one is data extraction errors. So while the previous one wasn't actually a bug, this would include, for example, okay, they change a name in one of their tables in their backend, so the scripts that they use to produce the intermediate database that then we query don't work anymore, and suddenly we don't have any more medications in our database. This happened 2 weeks ago. And suddenly, no patient is given medications anymore, so they're all very healthy, and then the software starts saying, yep, everyone can be discharged, no worries. Fun. So what we did, we built a very simple and very ugly dashboard using Flask. This is a really very simple one, but it's very effective. So what we do, we have all the parameters here, and we monitor, for example, the distribution of the parameters in recent past with the distribution in the historical data. So you see, for example, the average value in the past 500 measurements, and the accepted range that is based on some statistical calculation in the data that was used for training the model. If it's red, it means that it's outside the accepted range. If it's green, it means that it's good. We also, for example, identify parameters that haven't been measured recently. This was an addition after the medications table incident that I just told you about. So now if something is not there for more than a few days, it gets flagged immediately. So you see here we have different types of parameters that are monitored similarly, but not exactly the same. We can click on one of the columns, and we see the recent change in distribution. These are the limits, so this parameter is actually pretty okay. It's within the accepted ranges. And we can see also the distribution of the parameter in case we need to check, for example, for outliers, or if it makes sense and it's more or less what we expect. Example of a real problem. The average age for recent patients is outside of the confidence interval. So we click on the graph and we see this. So wow, so the average age in current, this is real data from previous weeks. The average age of patients is much lower than what we saw in the historical data. Any guess? COVID, exactly. So look at this, right? So we expect patients in the ICU to be more or less between 59 and 67, but now the average is quite a few years younger. Interesting, right? So if we use age as a parameter, as a feature of the model, this actually will tell the model that patients with COVID are actually doing better than they might be doing because they have a lower age. We also have a tab for predictions, so we can look at how the predictions of the model change over time. For example, the prediction at discharge, the prediction in the last 24 hours before discharge, and then all predictions. And also here we see an interesting trend. So the prediction at discharge, the percentage of prediction at discharge that were below a certain threshold of 1% became less and less. So that means that the model is giving higher and higher predictions in the past few weeks. This could mean a lot of things, but it's good to know what's happening to the trend in general. Let me have a sip of water. So next, we have interpretability and auditability. Now, we talk a lot about, explainable models, interpretability, which is all very true, but particularly when you work in a context that is very sensitive, not only for the life of patients, but also for legal reasons. So we need this, first of all, because the doctors might actually want to know what's happening, why is the model giving certain predictions to make more informed decisions. Just a percentage is not going to tell the doctors much. So already giving them the feature importance is nice, but we really want to enable them to have a full idea of why the model decided to say 7% and not 3%. If something happens, we must be able to provide all the information we can to any investigation. If a patient dies and the family sues the hospital, they will come to us and say, well, actually, you gave this prediction, so the doctor discharged the patient because they saw a low prediction, but then the patient died. So we need to be able to say, look, this is why the model said it, this is why the parameters of the patients were this and this. We need to show that we are fully aware of what the model is doing. And also, to put a model in production or a software in production in healthcare, you need certifications, and when you get audited, when you apply for certification, you need to show that you are fully aware and fully in control of what the model is doing. So in this case, explainability is not just a nice to have, but it's really a must have. And so this is something that we built with Streamlit. If you are a data scientist and you can be bothered to do any front-end work, Streamlit is great. It's very ugly, but it works very well. Amazingly ugly matplotlib plots, but you can build this in 15 minutes. It works, it does what you have to do. By the way, something I forgot, so both the one before and this are for now for internal monitoring, so doctors don't access this. It's for us to make sure that everything is going well. And the dashboard before will stay like that, whereas we would like, what I'm about to present now, we would like to also have, to open up for the user the opportunity to look at each patient in depth and how the prediction of the patient changed based on the changing features. So this is something that we show, so you can see the prediction over time, and we use SHAP for feature importance. I'm not going to go in details about SHAP, but I'm sure many of you know it. And we show how different features contribute differently to each data point. And then we also show here the value of the feature and how the feature importance varies with that value. To give you an example, you see this patient has had a quite low prediction probability, quite a low probability, and then it spikes up a little bit, and we see that it's mostly due to these two purple features here that weren't here, and then suddenly in the last 3 timestamps they pop up. So we're like, okay, the doctor might want to know why. Not only why is the probability at this level now, but why it went up from a lower probability to a higher probability. So if we look at these two graphs, you can look at the SHAP value. So this is basically a measure of feature importance, feature contribution, and of the feature value. So feature 9 is a measure of how awake the patient is, how responsive it is. And it dropped in value all of a sudden, so the patient is less responsive. The feature importance increases, means that the probability of readmission and mortality spikes up. So doctor sees this, like, now I understand. Because the patient is less responsive for various reasons, the probability that if we were to discharge this patient now goes up. And similarly for this one, this is interesting. So you see, there was no measured value for this feature until here, so the feature importance was done on an imputated value. But then as soon as the value is measured, we have more information, the feature importance goes up, the probability goes up because this value is actually above the median value for this a blood parameter. I'm hiding the names of the features because these are real patients, so we're trying to not show any individual case just for privacy reasons. And then last, prediction validity. So now we talked about parameters, features, we want to monitor that, but then given that those are correct, can we be sure that the predictions we make are indeed valid? So the sample that the model is trained on can be very different from the population on which the model is applied to in practice. So can this difference really produce a bias that makes the predictions invalid? To give an example, this is how the training set looks like. So we have admissions that start at a given time. Then we take the moment of discharge. and then the discharge can be either successful or unsuccessful. Build a classifier, we get a probability, and then the model is trained on this. In production, however, the model will give a prediction at any given point during the admission. So we actually provide the prediction every hour. But this prediction here is very far from discharge. And in the training set, we only have patients at discharge. So the doctors have given certain medications, have done certain actions to prepare the patient for discharge. So a patient at this point here can be very different from a patient at this point in terms of what they look like, in terms of values, in terms of interventions, medications, and so on. So we cannot really be sure that a prediction here is as valid as a prediction given just before discharge. So in general, when we talk about machine learning, this can apply to a lot of other contexts. We want to make sure that the instances of observations in production are similar enough to the training instances. Then a prediction is valid. And in the case of our model, we want to know, are the patients that are currently in the ICU and for which the model is providing a prediction right now, are they similar enough to patients that were discharged in the training set at the moment of discharge? So we have two main ways to make sure that this happens. One is very simple, so define business rules. So domain knowledge, basically. We sit with the doctors and we say, okay, these are the rules that, if they're true, then the patient is considered similar enough. And the second one is out-of-domain detection. So business rules means basically, okay, when is a patient eligible for discharge? If a patient is on life support, so for example, is on dialysis, is intubated, has some very strong medications, then those patients are never discharged from the ICU. So by definition, they are too different from patients that were discharged in the training set, and for those, we don't want the prediction to be used. Our domain is a bit more complex in the sense that we want to also be able to find patients that are not ready to be discharged without these rules. And those can be done with certain techniques like outlier detection or density estimation. There is a whole field of machine learning for this. And this is interesting because it can also detect novel patient types. So for example, if this model was in production when COVID hit, it would be hopefully able to tell us, look, the model has never seen this patient. Don't trust this prediction, or at least, be careful with it. So this is implemented in practice. This is still work in progress. It's the next step that we want to do. So it's soon to be implemented. This is the message that the user gets when they click on a patient that is not eligible for discharge. So we tell them the various causes that it could be. So you see that here the prediction is not shown, is because the patient is, in this case, on life support. So it's both intubated, is getting medications, and is on dialysis. Never going to be discharged. So it's actually, there's no point giving a prediction, not only because it's not safe, but also because it will decrease the trust that the user has on the software. If the software says, yeah, this patient can be discharged, but the doctor knows that the patient cannot be discharged, they will start losing trust in the software. And this, especially for doctors, is a very, very sensitive topic. We also monitor these business rules. This is the same dashboard as before. These are all the eligibility flags. So if any of this is true, we don't provide a prediction, or we give a warning at least. And we have, percentage of patients in the last 60 or whatever that have this flag, the mean length of the admission for which this patient was under this rule. So actually, more than half of the patients are intubated at least once, and for at least half of their whole stay in the ICU. If you're interested more in what we do for out-of-domain or out-of-distribution detection, you can check out this paper. It's online, so you can find it. Now, so we have all these rules. What happens if there is a problem? Now, I showed you a couple of cases. Okay, age is too low. We find that medications are not there anymore. What happens? So just a couple of cases. So if there is a data extraction error or a data registration error, so the very first thing we need to do is contact the hospital and say, look, this parameter is not there anymore. What's going on? Because we don't know whether it's because they changed the registration, it's because there is an error. because they just stopped measuring a doing a certain blood test, for example. That can also happen. And then depending on what they say, we then either need to ask them to fix it, or we need to add, for example, a row to the mapping of our extraction pipeline. Data drift, again, this is no one's fault. We need to discuss with the doctors to understand why there is this data drift. So, the answer could be, oh, well, these are COVID patients, or we stopped admitting patients with a certain disease, and so on. And if deemed appropriate, we might need to retrain the model, because if the feature that uses a parameter that is drifting a lot is very important for the model, then, well, the prediction is not valid anymore. So we might need to do a retraining. We don't do live retraining. We always retrain manually, because we need to check a lot of things. So yeah, it's not a good idea to do online training. What happens if we have an out-of-domain prediction? Well, I just showed you that. We just don't show the prediction in the front end, or we give a warning to the doctor saying, look, this patient cannot be discharged right now, so be very careful. What if a doctor flags a patient's prediction as abnormal? So we have a feedback button. We also want to put a little flag next to the patient saying, I don't think that this is true. Then we want to enable them to investigate the feature contribution and prediction to really understand why the prediction was given. And what happens if the distribution of the prediction start deviating from the historical one? So we know that the average readmission and mortality rate was about 6%. What if suddenly 15% of our predictions are above 10%? Then we really need to look at what caused this. Is the model calibrated well? Do we need to retrain it? And basically, we look at all the above to try and find the answers, which are often not very obvious. What's next? So I already mentioned we want to implement this out-of-domain detection as soon as possible, because it's very important. We want to automate at least some of the warnings. Right now, we only have the dashboard, so we need to check them manually. But maybe we want to get, an email or maybe a dashboard with all the warnings. This is difficult because we also need to be careful with alarm fatigue. So we don't want to be warned for every single time a parameter goes out of distribution. We want to monitor features, not only parameters. So, for example, all the aggregated features that we use as inputs to the model. This is very easy. Just didn't do it yet. We want to also monitor the missing text mappings. So, for example, some parameters have the ventilation mode that you're on, assisted, controlled, spontaneous, and so on. They use tens, sometimes hundreds of different text parameters, and we want to map them to categories. And sometimes they just start using free text to do this, and then we don't know what that means, and so we need to also monitor those. Monitor the outcomes and concept drift. So this is when, really like for example, the way of working in the hospital changes, and so suddenly their admission rate becomes much lower or much higher, and then the model is not actually reflecting practice anymore. And also something interesting would be the correlation and interactions between features. So how features interact with each other. Sometimes, for example, the pH in blood is very highly correlated with the amount of carbon dioxide in your blood. So if that, for example, starts not being true anymore, it might mean that the patients are different or the way they're treated is different. So to conclude, errors in data extraction can lead to unwanted model behavior. And that can happen because of changes in data registration or bugs in the hospital's code. And then we can have data drift due to changing populations in the hospital. And that also can cause problems to the model. And one of the big problems that is not caused by errors is that the model will provide predictions even though where predictions are not needed or when the prediction should not be used. And something that I want to highlight again is that explainability of the models is not only a nice thing to have because everyone talks about it, but without explainable models, we cannot go in production. Like it just doesn't happen. So in conclusion, a combination of UX design, monitoring, and mitigation processes, so what to do when problems are, very clear roles, very clear responsibilities, very clear process, are needed to be there to make sure that we can implement We can implement these models in the hospital. They can be used, and they can be effective and actually save lives, and not just be a nice advertisement for hospitals. So I think we have some time for Q&A. Thanks. And I get to throw this, which is, let's try. Okay. Nice.
Hello. I have a question about these ugly matplotlib graphs that you showed. I was wondering, how much time do you envision that one of those doctors would be taking to look at these feature importances and make a decision? Yeah, this one, for instance.
Yeah, it's very ugly, super ugly. Yeah.
And in an extension to that, can you comment on the challenge of informing these doctors with data visualizations that they might not be very familiar with in their day-to-day job? Like, how would that go?
Excellent question. So we would never show a doctor this exact plot. Yeah. So this is fully for us, implemented just for our own sort of debugging processes. This is very complex, especially if you don't understand feature importance, if you don't understand SHAP, and so on. So you see in the front end, this was already quite hard to even show just feature importance for the current prediction. Because you need to be able, these are actually aggregated features. So sometimes you have a feature like standard deviation of this parameter in the last 24 hours. How do you show it to a doctor, right? So, for example, we decided to exclude standard deviation features because we could not explain them. So we now only use, for example, the mean on the first 24 hours or overall. And we need to make it as humanly readable as possible. To do it that way, the reason why it's not in the software is because we haven't found a good way to do it. And so sometimes, often there is a balance between interpretability and simplicity. If interpretability makes the software very complex, they're not going to use it. If we don't have enough interpretability, they're also not going to use it. So there is a lot of user testing, and there's actually a huge difference, for example, between academic hospitals and non-academic hospitals. You go and do your user testing in academic hospital, and they're like, very cool, oh, I know SHAP, yeah, let's do this. And then you go to a normal hospital, and they're like, what? What's this number? What percent? I don't understand. And really, they don't understand, they don't want to understand, they're not used to these things. So it's not easy, and it is indeed a challenge to matplotlib or not matplotlib. I mean, if you use ggplot, it's going to be prettier, but not easier to understand often. So yeah, if you have good ideas on how to do it, come find me afterwards.
Yeah, sorry.
No, very good question. You can, pass it around.
Very nice presentation. It's really cool to see how far you guys have come in a few years, right?
Yeah.
The whole deployment stuff there is really cool. One question I had about the data is, where do you train on? Is this data from one hospital, or is this something you do for each hospital? Or?
Yeah. So for legal reasons, actually, we can only do it hospital per hospital. One of the many things we researched in the past is how to use, for example, the domain adaptation and transfer learning to try and use other hospitals without pulling the data together. By contracts, we are not allowed to pull data. But even if we were, it doesn't always increase the performance in the new hospitals. So we have to calibrate it hospital by hospital. So we have the software, but every time we want to go to a new hospital, we have to retrain the model. So we know which features are more or less, the predictive ones, but it can really change because, for example, in one hospital in Amsterdam, they have half of their patients are cardiac surgery patients. Those are patients that stay for 24 hours and then they leave. Almost no one dies. And then you go to, Utrecht, and they have, 30% are neurosurgical patients. Those are very difficult patients. Our model doesn't work at all on neurosurgery patients. So what do you do? Do you exclude them? Do you retrain? Do you calibrate? So yeah, we do it hospital by hospital.
Cool.
I think...